In the last class, we learned about selective mapping, partial transmit sequence, and interleaved OFDM. Uh, these methods, they are part of multiple signaling and probabilistic methods, where some sort of permutation happens within the OFDM sequence. And the sequence with the lowest PAPR is transmitted. So it needs an optimizer to work, an optimizer, a selection circuit to select the signal with the lowest PAPR. Now we'll learn about some other techniques. Please note that in multiple signaling and probabilistic techniques, uh, there is no loss of information. What we have seen in signal distortion methods, there is loss of information, but in multiple signaling and probabilistic methods, there is no loss of information. And the three methods you have studied in multiple signaling, that is selective mapping, partial transmit sequence, and interleaved OFDM. One of the disadvantage that happens in each of these circuits is that they need a side information to be sent along with the OFDM signal with the lowest PAPR. A side information which gives the information about which phase factor is selected, which sequence of phase is selected, or which interleaver is selected. Such information has to be sent along with the signal, along with the OFDM signal. And this results in reduction of data rate because we are using overhead bits. We want to send this overhead bits after every OFDM signal transmission, block transmission. The method we are going to learn today, that is tone injection, tone reservation, and active constellation shaping, and constrained constellation shaping. These methods have the advantage that there is no side information. There is no side information that needs to be transmitted. For tone injection, tone reservation, and active constellation shaping and constrained constellation shaping, there is not required a side information is not required to be sent after along with the OFDM signal. But it has the disadvantage that these methods, they increase the average power of the OFDM signal. They increase the average power average power of OFDM signal. So the advantage is that for these techniques, a side information need not be sent. So we have a better data rate when compared to the previous three techniques. These have a better data rate, more spectral efficiency. But the disadvantage is that while doing these operations, they increase the average power of OFDM. Sometimes the transmitter system becomes little complicated. Those are the disadvantages when you are using these techniques. We'll see each of these one by one. First, we are going to learn about tone injection technique. In this technique, the constellation size is increased so that each point in original complex plane constellation is mapped onto several other points in the expanded constellation prior to IDFT processing. So what happens is, this was the original constellation. You can see this diagram, figure 18, which shows the tone injection technique for a 16 QAM constellation. This was originally a 16 QAM constellation, so it has got 16 constellation points, 16 symbols mapped onto it, and a point on this constellation, for example, this point on the constellation, it is mapped onto several other points in an expanded constellation. So the original constellation, which has got 16 symbols, it is expanded to a higher order constellation like you see in the figure, and this symbol can be mapped to any of these constellation points. It can be mapped to any of these constellation points. Same is the case with every other point in this original constellation. Every point here, for example, this point here, which comes in the bottom left of this original constellation, it can be mapped onto any of the points on this extended constellation. So what happens is that when this point when this point it can be mapped onto any of these constellation points, two things happen. One is that a change in energy can happen. Second is a change in phase. Here you see in a constellation diagram, uh, when you talk about a constellation diagram, you have the real axis, you have the imaginary axis, and a symbol in the constellation, the energy of this symbol in the constellation is proportional to its distance from the origin. Proportional to the distance from the origin. So this distance from the origin, it actually gives you the an indication of the power. So this distance is d. This separation d is proportional to the energy of this particular symbol. And if I move this symbol onto some other point in the constellation, you can see that the distance has increased. Now it has got more distance, and you can also see the phase is different. The phase has become different now. The phase is different, and also the energy also has become different, right? So when I extend this point onto some other point like this, when I extend this particular point, when I extend this point here, or it can be here, or it can be here, or it can be here, can be here, it can map here, it can be mapped here, or it can be mapped here. What I am doing actually happening is that the phase and energy of this symbol is now different. So from the origin, now this symbol has got this phase. Now this symbol with a similar phase, but this symbol has got a different phase. This mapping has got a different phase. This mapping has got a different phase. This mapping is different. This mapping is different. This mapping is different, and this mapping is different. Okay, so I'll draw it a little more neatly. Okay, so this point can be mapped here, can be mapped here, can be mapped here, can be mapped here, Now you can observe two things similar to what I explained here. The energy has become different because the distance from the origin has become different. Okay, the distance from the origin has become different. You can clearly see the phase. If I draw lines from the origin, if I start drawing lines from the origin, you can clearly see the phase. So this symbol has got this phase, this symbol has got this phase, this symbol has got this phase, and like that. You can see that for each of these symbols, the phase has got different, and also the energy, the distance from the origin is different, which means the energy also is different. So if I what is the advantage if I extend the constellation in this way and I map the original constellation points onto a higher order constellation? So what is the advantage? The advantage is that when the phase and the energy changes, the PAPR also changes. You know that OFDM signal, the PAPR problem in OFDM signal is due to the addition of coherent phases, the addition of signals that have the same phase. And if you can make the phases different, or maybe you can if you can reduce the energy of the symbol points, then you can definitely vary the PAPR. If there is a high peak at a particular point, you could inject a tone. uh, Basically, this constellation point, when it gets extended to any of these other constellation points, you are increasing the energy of that particular symbol. And in OFDM, you know that a symbol is mapped onto a subcarrier. In OFDM, a symbol is mapped onto a subcarrier, and subcarrier is nothing but a frequency or a tone. A subcarrier is having a particular frequency or a tone. So when you are increasing the power of a particular symbol, it means that you are injecting a tone, you are giving more power to that particular symbol, or you are injecting a particular tone to make it uh, into a higher order constellation. You are increasing the energy of that particular symbol. So this technique has got the name tone injection. When you are mapping a particular point onto a higher order point in the constellation, you are actually increasing the energy of that particular symbol. Or in other words, you can say that you are injecting a particular tone, because that particular symbol corresponds to a subcarrier, which is nothing but a frequency or a tone. So this method has got the name tone injection. So you are injecting a particular tone and mapping this constellation point onto a higher energy point, higher energy constellation. So if you have a particular peak, if you have a peak at a particular point on the OFDM symbol, this point could be mapped onto here at this point, where you can see that the real and imaginary parts are negative, and this will have an impact in the amplitude of that subcarrier, and this peak could be brought down. By adjusting the power of the tone. You can increase the power in a positive way if you move upwards, or you can decrease the power. You can make the power more and more negative. The constellation points, the amplitudes can be made negative if you move downwards the constellation. So by adjusting the position of the constellation, so by adjusting uh, uh, throughout this various possibilities that this point can take, the subcarrier amplitude can be adjusted, and so the PAPR also can be adjusted. So I hope the idea is clear for you. In general, if you have a constellation with size m, so this is a constellation here, m is equal to 16. If I have a constellation with size m and its points are spaced by a distance d, here d is marked, d is the distance between distance between any 2 points in the minimum distance between any 2 points in the constellation, that is d. Then when you extend this constellation onto a higher order constellation like this, extend the original 16 QAM, when you extend the original 16 QAM constellation onto different points on the higher order constellation, you should be careful that the points on the higher order constellation should have a distance of at least d between the symbols, which means that when you extend this constellation onto higher order constellation, this distance, you can see this distance is this distance is the distance between the point in the original constellation and the point in the extended constellation. So that distance also should be maintained at least by a distance d. Otherwise, if the constellation points are too close to each other, and if the noise might affect these constellation points, and wrong detection may happen at that time. So in order to make the maintain the distance between the constellation points, this condition must be satisfied, where the spacing between each original point in the original constellation and its equivalent points in the expanded constellation should be at least d is equal to rho into d root m. So we have m equal to 16 here, m equal to 16, and so this expression can be reduced, can be written as d is equal to rho into d root of 16. So rho into d into 4. Let us see. Let us, for the time being, let us take rho as 1. Rho equal to 1, and so now for this constellation we have got d is equal to, so if I take rho as 1 and m equal to 16, I have got it as 4d, and this capital D is the distance between the original constellation point and the extended constellation point. So that is this distance. So this distance is d, the distance between the original constellation point and its equivalent point in the extended constellation. So that is the this distance d, and what is d? D is d should be at least equal to 4d. So you can clearly see. So from this point you have, from here to here you have d, from this point to this point you have d, this point to this point you have d, and this point to this point you have d. So you have 4d, 4 times d. What happens if d is less than 4d? If d is less than 4d, then these two constellations, they overlap with each other. They are constellation points. This original constellation and the extended constellation, their points, they have a chance that the points may get overlapped with each other, and we will not be able to identify. It will be very difficult for us to detect which is the point which got transmitted at the receiver. And what is the significance of this factor rho? Rho, we have taken it as 1, but rho can be even greater than 1. and if rho is greater than 1, it means that you have more distance of separation between the original point and the extended point. Okay, if I had rho, which is, if rho is greater than 1, we see that d is becoming a even more value. D will become greater than the previous one. D will become greater than 4d, and as such you can observe that the points will move even farther away. The constellation point will extend further outside, and as a result uh, you have a less bit error rate. So rho is taken as a value greater than or equal to 1. Now the kth QAM symbol on a single subcarrier with multiple constellation points, it can be represented like this. So xk tilde, which can be any of these extended points. Let's say this is xk tilde. Okay, xk tilde in general it can be written as xk plus pk into d plus qk into d, where d is the distance between the original constellation points and its equivalent constellation point in the extended constellation. And xk tilde, which is the point on the extended constellation, this can be written as xk. Xk is the original point. So this is xk, which is the original point, and xk plus pk into d plus qk into d, where pk and qk they are the variations along real axis and imaginary axis. So pk is the variation along real axis and qk is variation along imaginary axis, and this pk and qk they are integers. Pk and qk are integer numbers. For example, let me take some points and illustrate this to you. If I have taken point xk here, xk can be written as xk tilde can be written as xk plus so pk is the variation along real axis, qk is the variation along imaginary axis, and for this point you can see that there is no variation along the real axis. So you can write that 0, pk is 0 into d plus qk is 1 into d. So this xk I need to write I need to write the vector signs. Let me denote this by vector a real. Okay, and this or according to convention ax, and this is ay, and pk and qk are this 1 units. Pk and qk are like unit vectors. 0 into d into ax plus 1 into d into ay. So this is pk, 0 is pk and qk is equal to 1. So this original point xk, it has got no variation along the x-axis. It has variation of 1 unit, 1 into d along y-axis. So this point moves here. If I take this constellation point, you can see that there is variation along the y-axis, which is d, and again there is a variation along x-axis, which is again d. So this point can be written as xk tilde is equal to xk tilde is equal to xk, and this point has moved down. So you have -1 into d ax plus and this point okay, it is moving down along y-axis. Please note that it is moving down along y-axis. Okay. When you consider x-axis, this point has moved right. So when I'm talking about this point has moved right when I consider the x-axis. So I have 1 into d ax, and if I consider y-axis, this has moved down. So plus minus 1 into d into ay. Here pk is 1 and qk is minus 1. And similarly, you can map every point on this constellation with this expression, xk tilde is equal to xk plus pk into d plus qk into d. You can map any other point on this constellation. If you have a particular symbol xk, the extended symbols can be written in this way: xk tilde is equal to xk plus pk into d plus qk into d, where xk is the original QAM symbol and xk tilde is the point on the extended, equivalent point on the extended constellation. Okay, so that is the idea behind extending the constellation. Okay, now what are the disadvantages and disadvantages of this technique? The advantage is that there is no side information required to be transmitted. Okay. Before that, let me tell you what is the impact of increasing this energy of original constellation point. You can clearly see, if you map the original constellation point onto the point on the extended constellations, you can clearly see that the energy will increase. The power average power of OFDM signal will increase. Average power of OFDM signal will increase. That is one of the biggest disadvantages of this technique. And is there any side information required to decode this signal? Okay, any side information is required to decode this signal? No, because you can have this point A can be mapped onto A1, A2, A3, A4, A5, A6, A7 and A8. But this information, to which point it has been mapped, it doesn't need to be sent, because the receiver can decode the signal or the symbol using a modulo D operation. Okay, we are able to, the receiver is able to decode using a modulo D operation. Using a modulo D operation, the receiver is able to decode the original signal, which means you can simply divide this x tilde with D. You can simply divide this with D and pk and qk, so this term will perfectly divide with D, and you have a remainder as x tilde, which is the result of modulo D operation. So the modulo D operation will give you the original symbol x tilde, and as such you don't need any side information to get transmitted. So that is one of the advantage. Requires no side information. So there is no loss of bit rate. There is no loss of bit rate when you have no side information. And also the receiver only needs a modulo D operator. Receiver needs modulo D operations, only 2 modulo D operations. Receiver only needs 2 modulo D operations. The receiver complexity is less when compared to the previous techniques. The receiver complexity is less, but the transmitter complexity can be more. The transmitter complexity can be more. You can see that there is need of an optimizer to select the original constellation point onto which extended constellation it has to get mapped. So it needs an optimizer. The transmitter side needs an optimizer in order to decide that, and this optimizer can be little complex in nature. it can have complex circuitry, because you can see the number of constellation points it has now. Originally it had 16 constellations, and now it has 16 into 6 constellation points. So on the transmitter side, the complexity can increase. So that is another disadvantage. The transmitter complexity. Transmitter complexity is more. But again, the advantageous side is that the receiver complexity is less. So the receiver complexity is less. Okay, that is the advantage and disadvantage of this topic. The complexity of transmitter is the disadvantage. However, the receiver complexity is less, because a receiver has only modulo D operations. So how can you prevent these disadvantages? By cleverly choosing the extended constellation. Okay, by adjusting the value of D. Okay, by adjusting the value of D, but again D has got a trade-off. If you increase D too much, then the PAPR, we are able to reduce PAPR, but if you increase D too much, we are increasing the average power of the signal. If you reduce D, the PAPR will increase, the bit error rate will increase, but in that case, if you increase the bit error rate, then the signals will be in error. So increasing D, increasing D will result in increase of power, the increase of the average power of the signal, and this will reduce PAPR, but it will increase the average power. So let me write that here. So if D increases, then PAPR reduces, more flexibility is possible, but then the average power will increase. And if D decreases, then PAPR increases, and the bit error rate will increase. When D increases, if the PAPR reduces, then definitely the bit error rate will reduce. Okay, so you cannot increase D beyond a point, you cannot decrease D beyond a point. So you must cleverly choose the value of D, so that based on how much PAPR you are able to tolerate, based on how much bit error rate you require, and things like that. Okay. So I hope the idea of tone injection is clear for you. We'll move on to the next topic, tone reservation. Tone reservation. So tone reservation, all these tone adjustment techniques, they are basically have their subcarriers, the energy of the subcarriers adjusted. And in tone reservation is a technique in which a subset of tones is reserved for PAPR reduction, right? So when you have the OFDM signal, certain tones, certain subcarriers, maybe this subcarrier or some subcarrier, they are reserved for. So if you have subcarrier numbers 1, 2, 3, etc., up to maybe 64, some subcarriers, it will be reserved for PAPR reduction. It doesn't carry any information, some subcarriers are reserved for PAPR reduction, because if you adjust the value of subcarriers, we are able to control the value of PAPR. So some subcarriers, they are reserved for this PAPR reduction, to adjust the amplitudes of subcarrier and reduce the PAPR. And we have a time domain vector C that is added to the OFDM signal X, original OFDM signal X, and this C is chosen such that the PAPR reduces. So this X and C, the X is the OFDM signal, X is the OFDM signal in frequency domain, C is the this vector, this adjustment vector in frequency domain, and they lie in disjoint frequency subspaces. Okay, they lie in disjoint frequency subspaces, which means they are orthogonal to each other. So if for example, if I say X is having subcarriers x1, x2, x3, x4, x5, x6, x7, and x8, if I have subcarriers like this, C can be C1, C2, C3, C4, C5, C6, C7, and C8. And these X and C, they lie in joint frequency subspaces, which means that if I reserve certain tones for PAPR reduction, just like this tone, if I reserve this tone for PAPR reduction, I reserve, I don't, yeah, I reserve this tone for PAPR reduction, I reserve this tone for PAPR reduction, and I reserve this tone for PAPR. Suppose I reserve these tones X2, X4, X2, X4, X6, and X8 for PAPR reduction. We cannot use these tones for carrying the data. So, since they lie in disjoint spaces, this will be 0 because x1 carries data. This red colored, these x2, x4, and x6 and x8 are reserved. They are reserved for PAPR reduction. So these tones, the other tones, they carry data. So this has to be 0. This has to be 0. This has to be 0. Because they should lie in disjoint frequency subspaces. X1, X3, X5, and X7, they carry data, and this vector C, which is in frequency domain, it should not interfere with the original data. So when you recover finally at the receiver after FFT, when you recover this signal, this data should not, this vector C, capital C, which is in frequency domain, okay, both X and C, they are in frequency domain, they they should not interfere, C should not interfere with X, C should not interfere with the original data. Then what does C do? C adjusts these values C2, C4, C6, and C8. C adjusts these values in order to reduce PAPR, and X gets added with C. These two gets added, and then later an IDFT is taken. After X gets added with C, an IDFT is taken, and you get the equivalent time domain signals X and C. And you will see that even though C and X, they lie in disjoint frequency spaces, C doesn't interfere with any of the data of original symbol set X. You can very well see that this in time domain, C will have its subcarriers extended in order to adjust it in order to reduce the PAPR. Now, how will you find this value of C to reduce the PAPR? How will you find the value of C in order to reduce PAPR? So, it definitely needs an optimizer, and this problem, it can be implemented as a convex optimization. Convex optimization. It can be implemented as a convex optimization problem, where this expression, this using this expression, we are able to find the value of C. This expression finds the value of C which has got the minimum value of PAPR. Okay, I think time is up. So let me just finish my class for today.